Hello, my name is Toby Lee, and I come here with Professor Binay Kashani from the University of Colorado, Denver. And we come from the Big Data Management and Mining Lab. And today we bring you IBM, an intelligent bridge management tool for deterioration forecasting and anomaly detection based on physics-guided deep learning. So here's some background for you. Here we first quote the U.S. Department of Transportation, which they have said the National Bridge Inspection Standards require inspections at least once every 24 months for highway bridges that exceed 20 feet in total length located on public roads. So that contextualizes sort of the starting point of this project, in that we wanted to provide a solution for bridge asset management that could leverage data-driven tools as well as bridge evaluation and quantitative data that could help us inform resource allocation and prioritization of maintenance strategies. So as you can see, these are certain factors that affect bridge deterioration, things such as materials, design, daily traffic, and climate. And then we also have bridge report data, which are bridge evaluation data that are collected every 2 years, as mentioned in that quote. And so that has things like sufficiency ratings, condition ratings, year built, daily traffic, things like that, that quantitatively describe how a bridge is doing at a certain point in time, usually annually. And so after doing this initial literature review, looking at the data, we sort of came to the conclusion that we wanted to develop an end-to-end data-driven tool that could be used by DOTs, which leveraged deep learning as the modeling method, as well as the data that we mentioned previously, to provide some predictive power in this problem domain. So what is IBM? Again, as I mentioned, it's an end-to-end bridge management tool that's actually usable by an end user that does three things, or at least we envisioned it to do three things at the beginning. And this is what we seek out to do going forward. The first is bridge deterioration forecasting, as you can see from this illustration on the very left. These are curves for deterioration for bridges. So for example, these could be condition ratings, and they could be deteriorating over time. And our predictive model could pick up on these patterns and predict future unknown time steps and sort of forecast how a bridge would be deteriorating in the future. We also have bridge performance anomaly detection. So essentially, these are clusters of bridges based on descriptors and features. And we are able to identify here in the black outlined dots the outliers for these clusters. And so this might help for identifying bridges that are behaving in a way that an anomaly would and would be out of the norm. And at the end here, we have bridge family generation, which just refers to clustering this bridge data and deriving families or similarly behaving bridges based on the quantitative data, and we could better inform our resource allocation or maintenance strategies based on these generated families or clusters. So here we have an IBM System Overview. So this is the high-level view of what our system looked like at the beginning when we envisioned it, and sort of what we're working on currently. So here on the left side we have interface. So we have the ability to add model architectures for prediction. We have the ability to retrain these models on the data that we have. We have the ability to, of course, request a prediction. We have the ability to train these models from scratch, and then also add new data sources. And these are just the internal details. I won't go into them in too much detail, but essentially these are the functions that we had envisioned at the beginning. And so hopefully that gives you a good idea from the diagram there. And at the end here, we have physics-guided deep learning. Essentially, we wanted to incorporate some physics-guided functions for our models to sort of ground them. Sometimes what happens in purely data-driven models is they end up being very agnostic to the underlying principles of real-world phenomena and physics. So injecting a little bit of physics can ground them and guide them to actually provide predictions that are physically consistent with the systems that we're looking at. And so this is what this slide is pertaining to, sort of the combination of both purely data-driven and purely physics-based models to be able to leverage large data sets, but also still provide realistic predictions that are consistent with physics within the actual physical systems. And so that concludes my slideshow here. Yes, thank you for listening in.